Good day, everyone, and welcome to the U.S. Department of Energy's Fuel Cell Technologies Office webinar. We've got a great presentation lined up this month from Neha Rastagi and Amgad Elgowany from Argonne National Laboratory on the U.S. shale revolution and how the chemicals industry generates low-cost, large-scale supply of hydrogen. My name is Eric Parker. I provide program support within the Fuel Cell Technologies Office, and I'm the organizer for the meeting. We'll begin in just a moment, but first I have a couple housekeeping items to tell you about. Today's webinar is being recorded, and the recording, along with the slides you'll see today, will eventually be posted in the coming weeks, and we'll let you know. All attendees will be on mute throughout the webinar, so please submit your questions via the WebEx chat box that you should see on the WebEx panel. Here's an example of it here on the slide. We will cover those questions during the Q&A period at the end of the presentation. And with that, I'd like to introduce our webinar's host, Neha Rastagi, who is here with me at DOE headquarters. Neha is the lead for hydrogen delivery technologies within the Fuel Cell Technologies Office, and it's a pleasure to have you with us.
Thank you, Eric. So as Eric mentioned, our presentation will be from Dr. Amgad Elgowany. Amgad is a Principal Energy Systems Analyst and the Life Cycles Analysis Team Lead at Argonne National Laboratory. He conducts techno-economic and environmental analyses of alternative transportation fuels and advanced vehicle technologies, including hydrogen fuel cell electric vehicles. So our presentation today will be on fuels that can be used for fuel cell vehicles and are being produced in abundance as a result of the shale boom. And with that, I'll kick it off to Amgad.
All right. Take it away, Amgad.
Thank you, Neha, and thank you, Eric. Should I share my screen?
Yes, go ahead.
Can you see my screen now?
Yep, go ahead.
Okay, hello everyone. This is Amgad Elgowany. Today my presentation is about a near-term opportunity for low-cost hydrogen that could serve the early market demands of hydrogen. In particular, I will focus on the emerging demand of fuel cell electric vehicles. So, to put it in context, I am not sure if some of you have heard before about the H2 at Scale initiative. Dr. Brian Pivovar a year ago presented in this webinar the Hydrogen at Scale initiative and the concept there. I will provide a brief introduction here, but dive into the topic of the presentation. Hydrogen at Scale, as you see in this graph, trying to provide synergy across sectors. On the left, you see the power sector, which would be in the future dominated by renewables, but also nuclear power in the U.S. in particular is important, about 20% in the grid mix today. Electrons produced by renewable and the nuclear can be used in low temperature or high temperature electrolysis to produce the hydrogen molecules, which you can then serve different application. In one scenario, it could go back to serve the grid. In a low-term scenario, near-term scenario, it could be in a gas form injected into natural gas pipelines, and you see the transportation application in green here. Hydrogen fuel cell vehicles will be one of the leading demands, both in the near term and long term. And this will be my focus today, but other applications such as synthetic fuels, upgrading of conventional oil or bio oils, in addition to industry applications such as ammonia production or metal refining, could also be leverage the production of renewable hydrogen. So my focus will be on hydrogen fuel cell vehicles. The demand is expected to grow in the near term, especially in California, and then the zero-emission vehicle states in the northeast of the United States. And as the vehicle ramp up, there will be growing demand for the molecule. So vehicles are being deployed today, and here I put a couple of vehicles that are in the market today. On the left, you see the Toyota Mirai, rated at 66 miles per kilogram of hydrogen in the U.S. driving cycle. And on the right, you'll see the Honda Clarity, rated similarly at 67 miles per kilogram of hydrogen. Typical driving distance in the U.S. annually is somewhere between 12 to 14,000 miles. And on the average, a driver will drive a vehicle roughly 34 miles a day. Now, looking at the fuel economy, 34 miles or 33 miles is require roughly half of a kilogram per day. So if we understand the market penetration of fuel cell vehicles, we can calculate the market demand for a given vehicle scenario. So in California, for example, you will see the projected increase in fuel cell electric vehicle deployment, and within 5-year time frame, the projection is somewhere between 40 and 50,000 vehicles on the road. Considering a half kilogram per vehicle, then we are talking roughly about 20 to 25 tons per day of hydrogen will be required in California alone within a 5-year time frame. This will lead to an important question: where the hydrogen will come from? 20 tons a day in a given market would need to be satisfied with certain conditions. So it is important to understand where the hydrogen will come from and to look at opportunities for a low-cost molecule that will serve that market in the near term. And the idea here is to look for some source of hydrogen that is near term. Of course, we understand that the future is for renewable hydrogen, as I mentioned earlier, from zero carbon sources such as solar and wind and nuclear. But until we get there and until the economics and the market demand grows enough to make these technologies economical, we need something near term today that can serve these markets. So are there opportunities that can help with the transition as we ramp up the demand? So this is the question we are trying to answer today, and how this might enable energy security within the United States and promoting the hydrogen as an energy carrier, not only to serve the vehicle market, but to serve across sectors. So what will be the requirement of a near-term hydrogen supply source? First, we need the scale. We just talked in California, within 5 years, 20 tons a day. We need also the hydrogen to be produced in a high purity form. And in here I put greater than 80%. 80% is what we get from an SMR before the PSA purification. So if we get that high purity stream, then it will be economic to put a PSA unit to purify the hydrogen and supply hydrogen purity consistent with the requirement of fuel cell electric vehicles. We also need that in the near term we avoid large capital investment to minimize the risk of investment. And lower capital investment would result in a lower cost molecules. And we would like to make sure that we can produce a molecule competitive with the SMR cost today. We also want the molecule to be near the demand sites, whether it is on the West California or the Northeast. So the proximity of supply and demand will minimize the transportation cost. And finally, we need the molecule at least to be at par with hydrogen from steam methane reforming or better, and therefore we could leverage some of the incentives provided for a low carbon hydrogen. So what are our options today to serve the early markets? One option is to build a large-scale SMR plant in anticipation for a market growth. And this could be at a large scale, central, or a small scale if the demand is low and localized. Another option is to leverage some of the excess capacity, the marginal capacity existing today that is not being utilized in existing merchant plants across the U.S. And we will shed some light about what is the capacity of these merchant plants and what might the excess capacity amount to and the potential for that merchant market. And then really the core of this presentation is to explore the stranded byproduct hydrogen in existing industrial and chemical plants. And I will provide some quantitative numbers about the amount and the location of these potential hydrogen supply sources. So let us first eliminate some of these options. In the near term, building a very large SMR plants, 20 to 100 or 200 tons per day, require significant investments, hundreds of millions of dollars. And this will require, to invest in such a project, you would require significant demand, and also you would like some certainty of the demand and the longer-term contracts, which does not exist in the current market in California or other states. These plants also require long lead time to build and operate, to justify the investment, to get permitting, to design, and to construct and to put in place. So in the near term, this is not a viable option. And in the near term here, I mean the next 5 years, 5 to 10 years. So absent a large-scale plant, maybe a good option will be to build a small plant that satisfy a local demand, what we call distributed production or on-site production, at the scale consistent with the demand, maybe half a ton a day, maybe 2 tons a day, depending on the demand. This may be appropriate for a fleet operation, for example, a bus fleet, a fuel cell bus fleet, where you may have the consistent demand and you have the land area, and you could have depreciate your investment over the service of the buses provided over the years. However, this might not be as viable for a fuel cell light-duty vehicle market, simply because you shift the burden of capital investment to the station operator, who are usually small investors and risk-averse. Furthermore, you are adding capital which will be underutilized in the near term because these stations are not fully utilized as vehicles are being deployed gradually over the years. So the economics will not work. In addition, you will need significant footprint to install the on-site equipment. You will need purification. You will need maybe power upgrade. And all of these will deter that from being a viable option, absent few application, as I mentioned, fleet operators. So this is of limited viability in the near term as well. So how about hydrogen being produced today for refineries, and for the industry in general? And here I dissect the U.S. into 3 key regions. On the left, you see California, and you see there where are the different industries that use hydrogen. And you'll see also the blue triangle there. These are the liquid merchant plants. There are 2 of these in California, one in the north about 6 tons a day, and one at the south about 20 tons a day, combined 26 tons per day. And they already have their markets. In the Northeast, you will see several of these industries that use hydrogen, and the hydrogen is being produced there with one large liquid plant in New York with a capacity of 40 tons a day. However, the majority of the hydrogen is produced in the Gulf Coast, as you see in the middle, 7,000 metric tons per day, mainly to serve the U.S. refining industry. So we have a total merchant hydrogen capacity of roughly 13,000 tons per day. And out of these, a small portion, only 250 or 260 tons per day, are liquefied to supply the merchant market. If we consider the liquid hydrogen, which is really the dominant mode to supply hydrogen to several markets, in California alone, actually, we'll see that this is the non-refinery customers. And if we assume 10% excess capacity with the combined liquid plants in New York and in California, we are talking about a total of 60 to 70 tons per day. If there is a 10% excess capacity, then we are talking only 6 or 7 tons a day, which is capable of serving roughly 15,000 vehicles. And we are talking about 40 to 50,000 vehicles in California alone. So this has limited potential in the near term. So what we are proposing here is that there is significant production of hydrogen that is being stranded in industrial operation. And here I will show 2 examples. The first example is the chlorine plants. The chlorine plants produce roughly 1 million kilogram or 1,000 tons a day of hydrogen. This alone can fuel 2 million fuel cell vehicles. And here you will see actually the chloroalkali process here. You use electricity, mainly electrolysis, to separate the chlorine and to produce hydrogen. That hydrogen has several uses. Roughly half of it goes to the merchant market, which is the best use of the hydrogen molecule. In other cases where there is no market, it is combusted for process heat, and this is roughly 30 to 40%. And about 10 to 20% is being vented. So if we consider a 10% vented hydrogen of the 1,000 tons per day, we are talking about 100 tons per day. This can serve 200,000 fuel cell vehicles in the very near term. And this is a very high purity hydrogen. We are talking about 98, 90%, 99% purity. The other even bigger byproduct hydrogen comes from the cracker plants. And the cracker plants crack mainly ethane or butane or propane to provide the chemical feedstock ethylene or propylene or butylene. And in the process, you create a double bond and release hydrogen. That hydrogen is of high purity too, somewhere between 75 to 90% purity, very similar to the purities that you will get from an SMR before the PSA purification. Unfortunately, that hydrogen is being burned and combusted again for process heat and is being supplemented by natural gas, as you can see, to promote the cracking process. Now, in these 2 examples, that hydrogen can be set free and the thermal value of it could be displaced by low-cost BTUs of natural gas. So you can see really there is significant potential here. You have 1,000 tons per day from chlorine plants. You have 7,000 tons per day of hydrogen from cracker plants. combined 8 million kilograms that can serve 16 million vehicles. Here you can see where the chlorine plants are. And these are combined, again, produce 1,000 tons per day. You see they are fairly distributed, although a larger number of them is in the Gulf Coast, but you will see significant number of them in the Northeast and some of them on the West Coast. This could produce very high purity hydrogen, very low cost. And if you consider hydrogen that potentially could be vented when it does not have use, this is a green hydrogen molecule. This slide shows the cracker plants. On the top left, you will see the distribution of the cracker plants across the U.S. And on the right, you will see the concentration really in the Gulf Coast area. And there is roughly 51 ethylene production plants. This is just the ethylene ones. I am not talking about the propylenes or the butylenes ones. And these produce over 1.3 million tons of hydrogen a year, over 3.6 million kilograms a day of hydrogen. And this is, again, a high purity hydrogen. It is being stranded, it is being combusted. Hydrogen has much higher value than its thermal value. As we know, actually, we can compensate the thermal value with a low-cost, cheap natural gas. And the hydrogen can serve a bigger role in fuel cell vehicles where you can get the efficiency. So the proposal here is to make use of this stranded assets in a more energy efficient way. And as we have seen before, the fuel cell vehicles are at least twice as efficient as the fossil counterpart in internal combustion engine vehicles. So this slide shows really what would happen if you freeze a hydrogen molecule in a cracker plant. So if I set the hydrogen free, I need to compensate for its thermal value by supplementing the heating process with natural gas. And this is a very simple displacement. Natural gas is cheap, low cost, $3 to $4 a therm. A therm is 1 million BTU. I mean, last year it even dipped below $3 a million BTU. If we translate that to the displaced hydrogen, then you could really freeze the hydrogen at a very low cost. We're talking less than $0.50 a kilogram. If you add to it the cost of purification through PSA, and we did the techno-economics for that and also vetted that through industry, you add a small fraction, maybe 10, 20 cents at the most. So you are talking something in the order of $0.50 kilogram hydrogen produced from the PSA unit. And if it requires some compression, you may add another 30 cents or so. So all in all, we are talking at a high purity hydrogen molecule at less than $1 a kilogram that is large scale, that require no initial large capital investment. Some investment in a PSA unit may be some compression, but this is relatively low investment compared to the scale that you can produce and the cost you could achieve with this stranded asset. So here gives you a picture of the cracker plants existing and planned. In the next 3 to 4 years, the cracker plants will double. This is according to the EIA and the companies filed to build these plants. You'll see in particular the ethylene plants will double. And again, the majority of these are in Texas and the Gulf area, Louisiana, but you will see some are coming in the Midwest. You'll see North Dakota, you'll see Illinois, and then some will come in the Northeast. You see Pennsylvania, you see Ohio. So this will produce significant amount of hydrogen. We spoke with one of these cracker plants. We said, why do you not sell the hydrogen for a bigger value? They said there is no market for it. Where these plants exist, they don't see a big demand for hydrogen. This chart will show combine the cracker plants existing and the plant, and will show also the chlorine plant. Combined, they have the potential of 8,000 metric tons per day hydrogen. Again, this can serve millions of vehicles. Over 15 million fuel cell vehicles could be served just by these stranded hydrogen assets. And again, this is a larger scale, low cost, require small capital investment, and is fairly distributed. How about the environmental impact of that? We know SMR is at best at 70% today, lower heating value-based efficiency. So for each hydrogen BTU value or heating value, you need to consume roughly 1.5 BTUs of natural gas. Now the cracker plants will just displace a BTU as a BTU, as if it is 100% efficient. That efficiency gain will make the carbon footprint of hydrogen from the cracker plants to be 30% less than SMR. And remember that we crack fossil feedstock, in this case ethane or butane or propane. But the carbon we bring from the ground, we do not release in the air. It is locked in the product, the chemical feedstock, and the hydrogen is fairly zero carbon. However, because we compensate for the hydrogen with burning natural gas, we need really to burden that to the hydrogen, the amount of natural gas for a thermal BTU. But all in all, it is lower carbon footprint compared to the SMR, at least 30%. In some cases, it could be more. For example, you will see cracker plants can provide 25% to 30%. It depends really on how much compression and how much purification you may need. But if the hydrogen is vented and you make use of it, then it is a zero carbon molecule. And you may have a small penalty from compression, for example. And this is why you'll see a larger reduction if you could leverage and utilize some of the hydrogen that is being vented today. This slide shows the value of a low carbon hydrogen. This is, I borrowed from ARB presentation back in 2016, last year, by Sam Wade. And some of these values are proposed but calculated based on the carbon reduction potential. On the far right here, you will see the SMR. Even a fossil source of hydrogen generate credits under the low carbon fuel standards in California. You will see $1.6 a kilogram credit for gaseous hydrogen. You will see over $1 for liquid hydrogen. And this is all at $100 per metric ton of CO2, which was really the average price in 2016, as you see in the table above. So the credit prices kept going up from 2014 to 2015 to 2016. So at a higher price, you will get higher credits. And if the SMR can generate $1.6, then the hydrogen from the cracker plants can produce $2 because it is even lower carbon. And this is really $2 credit, while it costs you $1, then you could make money. Of course, the transportation cost is big and the refueling cost is big, but you could see you could offset some of the transportation costs with the credits you could generate in a market like California. So to conclude, the checkpoints here is that we have a large-scale production. We have a large-scale stranded hydrogen in these industrial plants. Fairly high priority, may require some investment in PSA to purify, but this is relatively low cost. This source requires low capital investment. Again, maybe some purification equipment. It is a low-cost molecule that can compete with today's SMR, and it even provides a better environmental footprint compared to the MR and can generate better credit. And these plants are distributed, and the upcoming ones, especially in the Northeast, the cracker plants can serve the Northeast market as fuel cell vehicles are deployed there. So with that, I want to acknowledge my colleagues at Argonne who contributed to this presentation, Dr. D.Y. Lee, Leah Talaber, Miriam Mintz, Michael McLemore, and Steve Folger. I want also to acknowledge DOE FCTO, the Fuel Cell Technologies Office, for their support of this work and for the H2 at Scale initiative in general. And in particular, I would like to thank Fred Josik and Neha Rustagi. Thank you.
Thank you, Amgad. Looks like we have a couple of questions coming in. So the first question regarded, so you discussed the cost of replacing hydrogen with natural gas at these chlor-alkali plants. Is there a cost associated with doing that to anything else, so to non-hydrogen products?
So I'm not sure about the question, but really the idea here is simple. Rather than burning the hydrogen, burn natural gas and freeze the hydrogen. So if I free a BTU of hydrogen, I consume a BTU of natural gas. So the cost of freeing a BTU of hydrogen is the cost of a BTU of natural gas. So this is really the point I was trying to make. So can you repeat the question? I'm not sure I understood the question. But
I think it's just to clarify that replacing the hydrogen with natural gas doesn't have any other impacts on the ethane or on the target product.
Yeah, I mean, especially in cracker plants, you already have the infrastructure. You have already natural gas is being used to supplement the hydrogen energy for the cracking process. So I imagine if there is any increase in demand for natural gas to offset the hydrogen, there might be some cost there. But if the infrastructure is there, then I imagine the cost will be low.
Okay. Another question was on slide 19, so I think we can scroll back to that slide. What carbon emissions are you assuming supplies power to the chlor-alkali plants?
So the power, I mean, the chlor-alkali plants have different technologies for producing the chlorine, and both of them use electricity. However, what I did here, you have different methods to allocate the energy and the emissions between the co-products. The most conservative one, to give credit to the hydrogen, is to say, well, after I produce the hydrogen, I use it for its thermal value. So what if I displace the hydrogen with natural gas, then I burden the hydrogen with natural gas that is compensating for the hydrogen loss. If I use a different life cycle analysis method, which really we do, then your carbon footprint will be much lower. So if I split the electricity use between the chlorine and the caustic soda and the hydrogen, then the burden on hydrogen will be much smaller too. And so there are different methods, and how you allocate based on energy, based on mass, because roughly for each ton of chlorine, 3% of that will be the mass of co-product hydrogen. So when you allocate by mass or by energy, hydrogen receives very little burden. So here I put the most conservative life cycle estimate of carbon emission associated with freeing the hydrogen and compensating it with natural gas. So other methods will show even a much lower carbon emission than what you see on this slide.
Okay, thank you. One other question came in related to delivery infrastructure. So if you can speak to the types of infrastructure that could be used to transport this hydrogen, would it be carriers like methanol, or what would be the infrastructure methods of interest?
So again, the thinking here is near term, how we can make things happen near term in a cost-effective way. And we are talking here about like next 5 years. So in that sense, is a traditional mode for transporting hydrogen, absent a very large demand that can justify a pipeline, then we are only dealing with trucking options, either gaseous trucking or liquid trucking. And the gaseous trucking, today you can carry a ton of payload with these composite tanks, lightweight composite tanks. You can carry a ton of hydrogen. And liquid tankers can carry about 4 tons of hydrogen. So depending on the distance and the transportation distance and the proximity of supply to demand, if you are within a couple of 100 miles, then gaseous delivery will be economic. If it is longer than 300 miles, if you truck, for example, from Texas to California, then it is over 1,000 miles, then liquid hydrogen will be more economical. And again, we are looking in the Northeast, perhaps gaseous trucking will be more viable because of the proximity of supply and demand. Trucking is costing today about, depending on the distance, for a couple of 100 miles, the trucking may cost about $2 a kilogram. If you go like several hundred miles, it may cost more. So the idea here is that if you transport to California and you are able to leverage some of the credit, it will offset some of the cost of transportation. So again, you may get $2 credit with GHG credits in California today, and this will offset some of the transportation costs.
Okay. One more question was, at what point will the hydrogen demand for fuel cell vehicles and lift trucks in North America begin to strain the existing hydrogen generation capacity?
So what we know is that today it is already starting to be a problem. As today, I believe we have in California about 3,000 vehicles. That is expected to more than double in the very short term. So, and then suddenly you will have a stress on the demand. So today, a lot of it is being supplied by the merchant market, by the excess capacity here and there, but this is very limited resource now. And as we push forward, then some companies starting to think about tapping into refinery hydrogen and pipelining it or purifying it, trucking it. So it is already a problem that has been mentioned in several forums and in several conferences, and at the California Hydrogen Business Council, this has been echoed in many, many places, that there is an urgent need to figure out where the next molecule will come from.
Okay. The next question, this is I guess more for our CTO, on whether or not the office has an interest in use of hydrogen for stationary fuel cells. So I can say, while the majority of our funding is focused on fuel cells for vehicles, we have funded a lot of stationary fuel cell work in the past, and we do have some ongoing projects in that space. The next question for Amgad is, what is the pressure that chlor-alkali or cracking plants are operated at, and whether or not those pressures would increase the cost burden to the PSA to purify the byproduct hydrogen?
Yeah, this is a very good question, and I alluded to that. The hydrogen from the chlor-alkali plant will come at very low pressure, a couple of bars or so, and it will require really compression to transport and to supply to a hydrogen terminal or a hydrogen liquefaction unit. But that cost is small, and I mean, our estimate of that is something in the order of 25, 30 cents. So in addition, actually, this is from the chlor-alkali plants. It is fairly pure, so it doesn't require a PSA there. For the cracker plants, it will require a PSA, and in fact, Neha shared with me yesterday a link that Praxair reported last year, this was in the news in 2016, that they are putting a PSA, and this is the only cracker plant I know doing that, putting PSA to purify hydrogen and supplying it to Dow Chemicals. So it does really has a precedent here, and it appears that it did make a lot of economic sense to do that from Praxair. The cost of purification and the compression combined is less than $0.50 a kilogram.
Okay, thank you, Amgad. Without any further questions, I think we will wrap up for today. So I'd like to thank everyone for joining us today and the thoughtful questions, as well as a big thank you to Amgad and Neha for their help today. If you didn't get a question, please feel free to email any of us on the slide you see. I also want to encourage everyone to sign up for the monthly newsletter that will inform you on future webinars. And you can find the sign up for receiving the recorded webinars and slides on that website as well. Have a great rest of your week, everyone, and goodbye.